So as I mentioned in the previous lecture, when we are dealing with breakdown voltage tests, we don't normally use the normal distribution or the Gaussian distribution because the data that we have in this case is not really suited for analysis, assuming a normal probability distribution curve. When we are talking about breakdown voltage measurements, there are two kinds of tests that we would be talking about. One is the breakdown voltage measurement. Here we ramp up the voltage at a particular rate, at a constant rate, and we note the voltage at which breakdown happens. So the random variable in this case is the voltage or the breakdown voltage. So you would have a probability distribution in voltage. That is one way. A similar test, which is kind of related, is the voltage endurance test. In the voltage endurance test, you take the insulator specimens and you apply a constant AC voltage and wait till failure happens. So the time to failure in this case is your random variable, and therefore you have a probability distribution in time t. Both more or less give you some kind of complementary data, complementary information. Now, in these kinds of data, we do not work with normal distributions, but we work with an extreme value distribution because breakdown is not determined by the average property of the material. Breakdown is a weak link phenomenon, which means that even if you have a single weak link, it is that weak link which is going to determine the breakdown rather than whatever is happening elsewhere. So all over the region, the entire volume of the material may be very capable of withstanding the applied stress, but if there is one small region which cannot withstand the applied stress, that is going to determine what the breakdown voltage will be or the time to failure will be. And therefore, for such kind of data, the probability distribution curve, the normal Gaussian distribution curve, is not an adequate representation, and therefore we use extreme value distributions. One of those extreme value distributions, which is suited or which is commonly used for breakdown measurement or voltage endurance test data, is the two-parameter Weibull cumulative distribution. The Weibull cumulative distribution function is given as f as a function of t, 1 minus exponential to the power minus t by alpha to the power beta, where it's not fx, ft, I'm sorry, where ft is the probability of failure if the specimen survives time t. So for time t, it hasn't failed, and then beyond time t, it fails. So ft is the cumulative probability distribution associated with the time interval t. Alpha is the scale parameter with the same units as t. So t by alpha is a unitless quantity. Bigger the alpha, longer is the time to failure. So alpha is a kind of measure of the peak magnitude of your Weibull value statistics. It tells Weibull value data. So it tells you how high the voltage, breakdown voltage is, what is the magnitude of the voltage, the mean value, or the time. So scale parameter is equivalent to the mean in the normal distribution. Beta is the shape parameter, and it is a measure of the spread of the data. So this is again analogous to standard deviation. So if you compare your Weibull distribution function with your normal distribution function, alpha is the scale parameter which tells you how peaked your peak magnitude is. So that is equivalent to the mean value in the measure of central tendency in normal distribution, whereas beta is the measure of the spread. So that is analogous to the standard deviation. It means that larger is your beta, smaller is the range in failure. So more peaked will be your curve. So if we go back to the curves that we had seen for the normal distribution, these are normal distributions, but if there were Weibull distributions, then this would have a higher scale. This again would also have a higher scale than, these three would have a higher scale than the magenta. So they would have a higher magnitude of the mean value. So this magenta curve would have a lower scale, just as it has a lower mean value. And the other three curves would have a higher or equal, higher than magenta and equal among themselves value of alpha. However, the red curve will have a high value of beta, that is, there is less spread, less standard deviation, smaller standard deviation, and beta will increase, beta will decrease as we go from the red to the green to the blue curve. So that is how you understand Weibull distribution. Generally, you expect the value of beta to be around 1 or 2 for voltage endurance test and around 10 for breakdown voltage test if you're measuring in kV. There are statistical packages which are available to compute the two parameters using the method of maximum likelihood. We are not going to learn how to do Weibull distributions here. It can be done. For a proper comparison between two materials, you should have an overlap between the confidence intervals, because it is not just the value of alpha which is important or the value of beta that is important. It is what confidence you have in a value lying between a certain range. So it is the comparison of the confidence intervals that we are interested in. And if you're going to say that this material is better than the material A is better than material B, you have to make sure the confidence interval of A does not overlap with the confidence interval of B, because if they have different values and still their confidence intervals overlap, then the confidence with which we can say that the value of alpha is the most probable value, or a range around alpha is the most probable value, will not give us any useful comparison between the two materials. Also, there are standards for analyzing sensor data for Weibull packages. IEEE 930 gives you the standards for analyzing sensor data. One thing I should mention is that the alpha value is the value not with 50% probability, but the value which has 63.2% probability. This is by convention. So 63.2% probability of failure, the voltage, or the time to failure, whichever it is that we are working with. Apart from the Weibull distribution, we also work with another extreme value distribution, which is the log normal distribution. The log normal distribution is more often used to analyze results of an accelerated aging test. So we are going to subsequently in this, while we are talking about testing and evaluation, we are going to discuss about accelerated tests. So right now I'm not going to talk about accelerated tests, accelerated aging tests. I'll come to that later, but log normal distributions are also used for breakdown voltage tests and tensile strength tests. Again, both of these are weakling phenomena. The statistical methodology for working with log normal distributions are specified in IEEE 930/1987. The logarithm of failure times or voltages are used as a random variable. So you will have xi, maybe the time to failure, or it can be the breakdown voltage. Whatever it is, we take the log of that and we plot the probability distribution of the log of that curve. Comparison of two types of insulation is possible. The one with the higher mean time to failure is the better one. Again, the confidence intervals should not overlap for a clean effective comparison, so that if you should be able to say with proper confidence that this is better than that, it is necessary that their confidence intervals do not overlap. Of course, time to failure if you're working with voltage endurance tests, otherwise voltage if you're working with the breakdown voltage. So these are the two distributions which are normally used for working with breakdown voltage data. Then we come to regression analysis. Regression analysis is generally used for lifetime analysis. So lifetime analysis, let's say for example, here I have example of data for thermal endurance graph for class B material. What is class B material? I'll come to later. Thermal endurance graph, what temperatures can that material withstand? Remember, dielectrics do not only have to possess dielectric properties, they also have to possess effective good non-electrical properties so that they can be used as good insulating materials. So if you look at the thermal endurance graph for class B material, what you have is, you have data here, 1, 2, 3, 4 points. These are data at temperature 200 degrees centigrade, 180, so somewhere between 180 and 200, and then 160. So all the data is clustered between 160 and 200 degrees centigrade. And from this we have figured out what is the time to failure. For example, for 200 degrees centigrade, time to failure is something in the range of 200, 300. This is probably a logarithmic scale, so 100, this might be 200 or 300. This is somewhere close to 800, 900. For 180 degrees centigrade, it is 1000. For 160, it is something like 2000. So this is all the data we have. Now we would like to know what is the time to fail, what is the temperatures that can be withstood for longer periods. So if this is your data, if you use linear regression, so you can use this data to, so you have the data from 200 to 160 degrees centigrade. You can extrapolate this data to predict the behavior of the material at much lower temperatures. So if you plot this line, you are using a linear regression analysis, you can see that you do not have data at lower temperatures for obvious reasons. You can see that if you were to apply a temperature of 140 degrees centigrade, then time to failure would be 10,000 hours. And if you instead went to 130 degrees centigrade, it would get to 20,000 hours. So these are huge quantities of time. You really cannot perform tests. So you cannot apply voltage and wait for 10,000 hours or wait for 20,000 hours. Instead, you can get the data for 1,000 and 2,000 hours, and from that you can try and extrapolate how many hours would a lower temperature be able to, the material will be able to withstand. But remember, linear regression cannot be performed for Weibull data, and for that we have to use more complicated regression analysis, and there are statistical packages which might be necessary to perform regression analysis with Weibull data. Here I have been talking about extrapolation. I will just say that these techniques, the statistical techniques are important while working with lifetime data and while we're working with accelerated aging tests. I'm going to discuss accelerated aging and regression analysis a little. I'm going to talk about accelerated aging and lifetime analysis a little later. I just wanted to point out that from the statistical point of view, there are statistical packages available which will allow us to perform regression analysis so that we can use the data for certain times or certain temperatures to extrapolate and predict behavior at other temperatures or other times. Now, if we talk about the various laboratory test procedures that can be used, especially for dielectric breakdown tests, it will also give you an idea about performing other tests, but we will limit our discussion to failure, breakdown, or puncture test. There are three commonly used methods: the multi-level method, the up and down method, and the extended up and down method. In the multi-level method, we a priori choose several test levels. So from the engineering viewpoint, we should have some idea about what are the test levels that we expect our material to be able to withstand. If you're working with air, we don't expect it to be able to withstand voltages like 100 kV per centimeter or so on. If you have a 1 centimeter gap, you're not going to expect to apply 100 kV. You probably would know that you're going to apply something like 10 kV, 15 kV. So you choose several test voltage levels appropriately, and also decide on a pre-specified number of shots. How many shots do you want to apply at each level? This again comes from engineering judgment and from experimentation. Let us say I have decided on a pre-specified number at each level of n. So that means I take a particular voltage V1 and I apply voltage V1 for n number of times. Then I go to voltage V2, I apply voltage V2 across the material for n number of times. So every voltage level is applied for n number of times independently, and these should be separate equivalent samples, similar samples, but cannot be the same sample, because once you stress the sample, you're changing the conditions in that sample. So each of them have to be virgin samples. Apply a pre-specified number of shots at each level. Count the number x of breakdowns at each level. So suppose out of n, you have xj number of breakdown. Then plot the probability of PV as xj by n against voltage. So on the y-axis, you have the fraction xj by n, where xj is the number of failures and n is the total number of shots. And on the x-axis, you have the voltage in kV. Draw a line of best fit on a probability scale. From the line, determine the voltage at which the cumulative probability is 50%. Determine sigma as V 50% minus V 16%. And this way you will be able to determine the confidence interval of plus minus 3 sigma, which will give you the statistical Wheatstone voltage and the statistical over voltage. And you have the probability distribution. Now the advantage of this method is you're just taking the data and you're plotting it. So all you're doing is you have V and you're plotting P of V as a function of the number of, as a fraction of the number of breakdowns. So you are not assuming the normality of the distribution. You're working with a distribution that is automatically obtained from the data. The disadvantage of this method is that it is time consuming. This test method is generally preferred for research and live line testing. Typically, we work with 100 shots per level and we work with 6 to 10 levels. The next method that we will discuss is the up and down method. In this case, this is the algorithm. Pick starting voltage V1 is equal to VI. Again, you have to choose a voltage which is meaningful. You do not choose 100 kV for air because it will only lengthen your process. It will make your process time consuming. So intelligently pick a starting voltage V1 is equal to VI. Now choose a delta V. So how fine-tuned do you want your voltages? Are you okay with a voltage breakdown strength plus minus 1 kV? Or you want it closer 0.5 kV? So depending on this factor, you choose your delta V. Then apply one shot at VI. There are two possible outcomes, breakdown or Wheatstone. If breakdown happens, tune down the voltage. So if breakdown happens at, let's say you are at this level, V0 plus delta V, and you apply the voltage. At the first shot, you have failure. If you have failure, you bring down the test voltage to VI minus delta V. So now you're at this level. Apply shot 1, apply next shot. When you apply next shot, there are two possible outcomes, Wheatstone or failure. Let's say you have applied one shot. If there is failure, you would want to come down, but let's say there has been Wheatstone. So if the second shot, which is at V0 minus delta, VI minus delta V has been withstood, you again up the voltage. So now again you are at VI plus delta V. Let's say this also has withstood. So this is because of the randomness of the test. So at the same voltage level, there has been one failure, one Wheatstone. When there has been one Wheatstone, you again notch it up by delta V. Again there is failure. The moment there is failure, you come down. So whenever there is a failure, you come down by delta V. You bring down the voltage by delta V. And every time there is a Wheatstone, you up the voltage by delta V. And in this way, you continue for a large number of shots. So this will yield your probability distribution. V0 is the lowest level at which voltage is applied. So you're not working below this level. So this is the algorithm. Whenever there is a breakdown, you reduce the voltage, test voltage. Whenever there is a Wheatstone, you up the test voltage. And in this way, you get the probability distribution curve. Because, for example, here you can see there have been 1, 2, 3, 4, 5 shots at this particular level, V0 plus delta V. And out of these, 2 have been failures and 3 have been withstood. So you will be, from this, you will be getting a probability distribution curve. Putting these two methods together, we have what is called the extended up and down method. This kind of combines the advantages of both these previous methods. So we select the highest or the lowest voltage that we want to measure. Let's say that is 940. And we also decide what is the specified number of tests at every level. Let's say n, that is n in the previous case. Let us say that we have chosen n to be equal to 7. So at 940, we apply 7 shots. And all 7 shots have been withstood. So we up the voltage by delta V. In this case, as you can see, we have taken a delta V of 30. Again, apply 7 shots. Withstood. Increase. Again, apply 7 shots. Again, no breakdown. Again, increase. Now, in this case, when you go from 1000 to 1030, what we see is we are intending to apply 7 shots, but the first shot is a failure. The moment it is a failure, we go down by delta V. So in this case, we do not wait for the 7 shots. The moment there is a failure, we go down, we reduce the voltage. So in this case, there has been a failure in the first shot, you reduce the voltage. Again, you go back to 1000. In this case, you had 7 shots and no failure. Now when you apply, the first shot is withstood, the second shot fails. So 1 out of 2. As soon as there is failure, you go down. But at 970, there is no failure. So again, you come up. So the idea is that if there are no breakdowns, you apply all the 7 shots. If there is breakdown, whenever there is breakdown, you reduce the voltage. And you calculate what is the probability. So in this case, 1 out of 1 is the probability. Here it is 1/2. This is 0 out of 7. Now you have half here. Next time you have 1/3. So associated with each test at each level, you will be getting a probability distribution. The number n is determined such that a series of n would have a 50% probability of giving at least one flashover. So, I mean, here you don't choose ridiculous value so that you go on applying the voltage and you're never going to get failure, or the moment so that lowest voltage should not be much too lower than the expected breakdown value. And in this way, you calculate the probability distribution curve. So these are the 3 different techniques in which breakdown strengths are used. Apart from that, this is all about the statistical analysis that we use. In the next lecture, we will discuss about some of the tests that are routinely done on insulation.